Okay, this is a nice long report. Comes from a company that is owned by partly by the French government and a bunch of other private investors. It says Emerging Sustainable Technologies Edition 2024 focuses on the ocean, as you can see in the background. It's very broad in terms of the topics it covers, so I'm not going to go into the details. I'm going to just give you sampling of all the various topics of ocean exploitation. We don't want to use word like exploitation. You want to say sustainable ocean harvesting. Ocean gives us energy, it gives us food, it gives us medicines, it gives us ecotourism, and of course all the rain we get mostly is evaporation from the oceans, and it also takes up more than 90% of all the additional energy we are trapping by increasing global greenhouse gases, which means global warming is not at all as strong as it could be if the ocean wasn't taking up more than 90% of this energy, right? So here is the overview of technologies that are presented in this document. Gives you a sense of the breadth of the coverage. So here is a sedimentary cover and continental crust and continental shelf. There are definitions for shelf that you can go and read. I have oceanography course where you can find it as well. Desalination, of course, mineral recovery from brine. So lithium is being done this way, or proposed to be done in a sustainable way. Osmotic power. On the continental shelf, we have tidal energy, wave energy, ocean thermal energy conversion, and ocean-based negative emissions technologies, or ocean CDR as it's called, ocean carbon dioxide removal. Although these technologies are here presented as separate chapters, they will in most cases not be deployed as standalone. So desalination will be combined with something else, and it will be done with solar energy or offshore wind and so on and so forth. They will be integrated in the system of systems approach, which is the key for a successful energy transition and sustainability overall. So here we are with marine floating solar power, direct ocean. So this is the pieces of getting into these now. Floating solar power, so just like offshore wind, you can have massive floating solar power. If we remember that the ocean covers 70% of the surface area, it has so much space to offer in addition to land. Of course, you have to think of how the energy can be moved on to land and away from the coast into inland and so on and so forth. Large energy storage, of course, ocean has a huge heat capacity, water has a huge heat capacity, and it stores tremendous amount of energy. So it's like a natural battery if we can figure out how to use it. Again, continental slope, continental rise, abyssal plain, and deep sea mining is now becoming more and more, with lots of concerns about impacts on biodiversity and other things. And ocean has a massive storage or storehouse for DNA, all kinds of species that live in there. So can we do something with that as well? And direct ocean capture of carbon dioxide, and you have increased alkalinity to take it down, or you have other ways that I've discussed in a series of podcasts already, so I'll not go into details here. So you have offshore molecular production as well for various applications like synthetic fuels that we can look at, and there is also deep sea storage that is possible. So just in terms of timelines, growing interest in ocean energy in recent years. From 2020, there are reports from Mission Starfish, Restore Our Oceans and Waters. IRENA has a report on innovation outlook for ocean energy technologies, and Ocean in Humanity's Future, Nature published that. There have been conferences, there have been other reports by 2021 about Ocean Europe, Ocean's Future 2050. There is a UN decade of ocean science going on now, 100% sustainable ocean management, other conferences, and 2022 also has more reports, more conferences, and 2023 follows up with more reports and conferences, and I'm recording this in 2024 and the report came out just a few months ago, so there are already some conferences. So the first topic here is offshore renewable energy production and storage technologies. As I said, just look at the topics, follow up with the report if you are interested in more details, because I'm not going to go into a lot of details, but there are analysis provided as well for cost benefit analysis and pros and cons and other things. So ocean energy, you have osmotic power, tidal and ocean currents energy, wave energy of course, ocean thermal energy conversion that we mentioned, OTEC, marine floating solar power we mentioned, offshore molecules production, large energy storage. Okay, so using the salinity of the oceans to produce sustainable and clean energy is imagined here. You have ocean water, osmosis of this obviously works by having a semi-permeable membrane that moves minerals or dissolved material from one side to the other. So you have solute molecules here, osmosis movement of solvent from low to high solvent concentration. So you move the solvent instead of the solutes. So you move, if you have less solutes on one side, you have more solvent, so you can move the solvent to the other side. You can see this volume is increasing and this volume is decreasing, and the solutes are remaining right there. That's the basic principle. So here is a pressure retarded osmosis PRO process. I won't go into the details. As I said, there is a semi-permeable membrane. There are pumps that take in high saline water and fresh water and do osmotic pressure forces with fresh water into the high salt water, and then pump it into the turbine, produce energy, and so on and so forth. You get the idea. Basically, it's osmotic power. Use the naturally available salt water with fresh water to do osmotic pressure driven energy production. Ionic nano-osmotic diffusion membranes are used in these technologies, and they have the advantage that environmentally friendly biosource materials are involved and continuous and abundant source of these things. So they rely on nanoscale membranes coupled with electrode systems. These membranes combine high ionic selectivity with high ionic transport to improve performance, and there are also modular ways to do these things. So coupling of osmotic power and desalination towards circular economy is imagined. This integration contributes to the decarbonization of the desalination process by increasing its energy efficiency and recovering renewable electric energy and raw materials from brine. As we said, they will not be very unlikely that they will be doing only one thing like desalination or osmotic power, but you can combine them, and we'll see other examples. Tidal energy technologies are the closest to market ocean energy solutions. So tidal currents are the result of the ocean water mass response to interactions between the moon, sun and the earth. Their magnitude depends on the distance from the sun and moon from the earth. Good things, but there are also places where massive amplification of tides happens in the Bay of Fundy and so on. So you have very well-known points where tidal energy potential is very high. Question of course is, there are also technologies where tides come in and drive the turbine, and tides go out and can drive the turbine, and so on. So this technology is quite mature in terms of technology readiness level and already implementation happening and so on. Wave energy technologies range from laboratory prototype stage to the pilot stage in real sea conditions. Wave power, of course, converts the periodic up and down movement of ocean waves into electricity. These are often driven by winds as opposed to tides driven by lunar and solar gravitational pulls. In wave energy, there is a great design variety with no dominant sub-technology. So I will just read it, and there are technology readiness levels mentioned there as well. The 8 families of wave energy technologies: point absorber at TRL 7, oscillating water column TRL 8, which is very high, attenuator at TRL 8, overstopping TRL 5, oscillating water surge converter at TRL 7, rotating mass at TRL 7, submerged pressure differential TRL6 and bulge wave at TRL5. There is short descriptions under each. For example, bulge wave is a semi-submerged flexible device which relies only on the surge as it is placed parallel to the waves. Okay, so all details are there, very nice. Okay, so here is an example of OTEC process, ocean thermal energy conversion. You have an open cycle and a closed cycle system. So you have a pump which takes in the water, flash evaporator to remove the water, and drive a turbine and produce electricity and put the remaining water back into the condenser and pump it into the ocean. And there is a vacuum pump which does the work in terms of what to do with the water after it's done with the electricity production. It's an open system, but here you have a closed system in terms of evaporator, energy production, condenser, and recycling it. There are advantages and disadvantages that you can go and read, but again, I don't want to get into the details. There's also a hybrid cycle which does open and closed cycle. So the legends for these are warm seawater, cold seawater, and working fluid. So there is some kind of a working fluid when you have a closed system, closed cycle, and non-condensable, so drops out here, puts back in, or goes into a condenser, and desalinated water is taken out here and put back into the system or ocean. So you're not taking out water, you're just using it, desalinating it, converting to energy and putting it back, closed or open or hybrid cycles. Okay, so seawater air conditioning systems are, I think, already implemented in many places because you have cold waters as you go below the surface. You can take it in, it's coming in here, and the effluent seawater is put back in. And if you're running it into a heat exchanger cooling system where your building, let's say, is getting the chilled water supply by basically using the naturally available deep sea waters in terms of the temperature differential. So this is a warm building, you want to take the warm air out by chilling, and that's what you are using the deep sea water for. Okay, key components of a floating photovoltaic system, modified and reprinted with permission from some company in NTU in Singapore. So again, without going into much detail, PV modules to convert light into electricity are sitting here. Lightning protection is needed, of course. Floating structure has a mooring line. There is a combiner box, so inverters to convert DC into alternating current for consumption. So as you know, PVs produce DC. You need AC for most applications because of transmission and other things. From other arrays, energy is also feeding back. So here is the transmission line. There are underwater cables bringing it onshore. So there are transformers to increase voltage to reduce electrical losses. These are standard transmission technologies. Okay, so large offshore renewable energy potential and CO2 availability in the air or in the sea offer an opportunity to synthesize e-fuels. E-fuels production uses green electricity to electrolyze the seawater and run direct air capture and direct ocean capture systems to provide CO2 for their synthesis. Okay, so kind of a CCUS system, carbon capture and utilization and sequestration system. Okay, so this is how e-fuel synthesis would work. You're using renewable energy, taking seawater, doing pre-treatment, doing the electrolysis and air separation unit, producing the Haber-Bosch process, which is famous for producing ammonia, which is at TRL7, so that's called e-fuel here. NG is the company that we are talking about, and there is a direct air capture or direct ocean capture, and hydrogenation happens to produce e-methanol, e-hydrocarbons, and e-methane, and this is in the range of technology readiness level of 6 to 8. Very brief, but you get the idea of the directions and levels of expertise and technology advancement. Different models to integrate offshore wind and PV with hydrogen production for offshore E-molecule productions. molecules production. Offshore renewable energy from a farm with onshore electrolyzer here, centralized electrolysis happening, producing H2 for e-fuels. And here you have offshore renewable energy from farm with decentralized electrolyzer, as opposed to bringing it on land. You do it on the ocean itself and bring H2 onto land, of course. Offshore renewable energy from a farm with centralized offshore electrolyzer. So just various designs. The TRL level is not given here, but offshore green hydrogen production is shown here. Again, green hydrogen basically is where you are doing electrolysis with renewable energy, and sometimes they also talk about capturing any CO2 that's produced. So direct seawater electrolysis is a process where the usual demineralized water is used to conventional electrolyzers to replace seawater, to be replaced by seawater. Let me read it again. Zoom on direct seawater electrolysis option. Direct seawater electrolysis is a process where the usual demineralized water used in conventional electrolyzers is replaced by seawater. Of course, seawater is plentiful, and you have a lot of area over the oceans to produce renewable energy as well, to do green hydrogen. So you are using direct seawater electrolysis here, and here you are using renewable energy to do high pressure pumping of seawater, doing some pre-treatment with membrane module to produce, taking the brine and producing permeate, and then doing conventional electrolysis of water as opposed to direct seawater analysis. E-methanol, an alternative for marine transport fuel, transportation over the oceans. They produce contrails, which is bad for trapping thermal energy, but also they are dirty. It's a dirty business, so you want to make the fuels cleaner. So this is showing some reactions to produce methanol. So conventional methanol production happens through natural gas reforming to produce syngas, which is then compressed, put through a methane loop, and methane distillation done to store it and use it. Whereas here in the alternate methanol production, you are taking fuel gas, doing carbon capture, taking feed water, doing electrolysis, producing H2 and CO2, doing compression to produce, put into the methane loop. Instead of getting syngas, you are putting CO2 and H2 separately, and doing again crude methanol here to methane distillation and methanol to storage. I'm just running through these because the ideas are good. I want to show them, but you have to read if you want more detail. Offshore energy, offshore power to X. So illustration of the conceptual wind-powered PTO to P2X platform for methane to methanol production. So electricity from offshore, reverse osmosis, electrolysis process, wastewater treatment, methane to methanol, and then solid waste is put back out. E-crude for e-liquid hydrocarbon synthesis. Similar ideas without going into details. E-ammonia is among the top contenders with marine fuel of the future. Ammonia is already transported by ship as cargo, meaning many marine actors are familiar with its use and handling, so no new training may be required, but again you have an idea, schematic of how this system of producing e-ammonia would work. Okay, so if you want to think about energy storage technologies, power capacity versus discharge duration, so ocean as an energy storage system. So you have mechanical, thermal, electricity, electrochemical, and chemical processes involved. There is a discharge duration going from seconds to a season, right? And here you have typical power capacity going from 1 kilowatt to 1 gigawatt, right? So reserve and response service, transmission and distribution grid support, and bulk power management. And the components are thermal energies, that's here, and you have bulk power management with hydrogen storage, mechanical energy storage, pumped hydro storage, where you use intermittent energy to pump some liquid or water up the slope and then let it flow down when there is intermittency by gravity, and then you can use it to drive turbines, produce energy, and so on. There are details given for each of these in the text that I'm skipping. Flywheels energy storage system, where again excess energy or produced energy when solar and wind are available can be used to do energy storage in a flywheel system. Here are some supercapacitors, superconducting magnetic energy storage, and so on and so forth. All these are easily done with the ocean. Innovative large-scale desalination, mineral recovery from brine, mineral recovery from the seafloor, and so on. Affordable large-scale desalination, how do we get there? Key technological breakthroughs are expected, reducing water costs for drinking purpose and energy transition while minimizing the environmental impacts. Good goals. There are new processes, advanced membrane materials, and integrated solutions to drive main innovative desalination technologies. Everything has pros, cons, cost benefit analysis needed, life cycle analysis needed. Even if you produce a lot of water, clean water at the coast, how do you move it to give it to people inland in a big country, for example, right? So you can also do minerals extraction, of course, minerals and seawater. There are processes, so you can think of chloride, sodium, sulfate, calcium, potassium, rare minerals, magnesium. Of course, the challenge is that concentrations can be very low, so economy is always a concern. You can use the brines to produce fresh water, minerals, metals, and salts. You can move it to the market or remineralize chemicals, energy, CO2, and e-fuels that we already talked about. There are, of course, risks, supply risks sorted through largest to smallest. So here are all the various things: magnesium, niobium, germanium, borates, scandium, strontium, cobalt, PGMs, natural graphite, indium, vanadium, lithium, tungsten, titanium, gallium, hafnium, silicon metal, manganese, chromium, zirconium, tellurium, nickel, copper, right? So they all can feed into batteries, fuel cells, wind, PVs, robotics, 3D printing, and ICT, internet and communication technologies, and feed into the renewable sector. Okay, so nice analysis, lots of optimistic messages, but you have to remember it's a company that's profitable or profit-making company, so they obviously will sell to investors ideas that may be not as technology ready as they claim. Okay, but let's not worry about it. Here's the concentration in brine seawater of any particular mineral or so you are extracting. Here are all these things. I won't read all of them: cesium, rubidium, uranium, iodine, lithium, boron, calcium, potassium, magnesium, sodium. So here are the prices in kilograms. Obviously, as concentrations increase, prices drop, and here it will be very economically challenging if the concentration in this range. But if the concentration in this is in this range, then they can be economically feasible. So even when prices are high, it can be economically feasible based on other considerations of where it's used. Finally, coming closer to deep sea deposits, I won't go into the geology, but basically wherever there are vents, crusts, the system produces nodules which have all these valuable minerals that countries like China and India are trying to mine. Lots of debate about whether that's a good idea or not, but here are some additional informations on how deep sea mining would work. You have a jet type hydraulic collecting system, so you are taking nodules and pumping from the polymetallic nodules. You are extracting what you need and then dumping back what you don't need. And pump type hydraulic cooling mechanism, so a suction pipe that will just suck up the nodules. A lifting pump is introduced to suck in the nodules near the opening of the collecting tube. Hydromechanical composite type, and so on. But you can see that this is big business. These are all the countries where various stages of deep sea mining are happening. Polymetallic sulfide, 7 contracts, current exploration licenses 2033. Cobalt rich ferromanganese crusts, 5 contracts. Polymetallic nodules, 9 contracts. And pretty much every country is involved in it other than maybe the poor Africans. Okay, so I won't go into the details there, but ocean based negative emissions technologies we already discussed in terms of putting more CO2, enhancing ocean CO2 uptake. Calling them negative emissions is kind of maybe not very accurate, but there is deep sea ocean carbon storage, iron fertilization and phosphorus fertilization, alkalinity enhancement, seaweed cultivation and sequestration, and coastal blue carbon. I have discussed each of these separately in podcasts, so I won't go into those here, but basically you are using natural chemistry of the ocean of moving H2 CO2 dissolves easily, H2O plus CO2 gives us H2CO3 is split into HCO3 minus and then carbonate, but if you increase CO2, carbonate ions begin to get depleted, which is bad news. That's what ocean acidification is, but ocean wants to maintain a pH, so you can use that to induce high and low pH waters to drive these reactions, to drive ocean CO2 uptake. Okay, so there are acid routes, so reduced pH, and alkaline routes, increased pH. Okay, I have discussed that elsewhere, as I said, so I'm not going to go into that detail here. So it's a bit long, but that's okay. It's something I wanted to cover in one podcast, but you can go and read the report, which is very long and has a lot of nice details, but this introduction should be useful just in terms of giving you a range of resources and opportunities to harvest the oceans sustainably. Okay, see you in the next topic.